The confidence interval for a population proportion has a very similar procedure, all right, and similar formulas, setup, process. But obviously it is just slightly different because we're no longer talking about a population mean. Now we're going to be discussing a population proportion. All right, so a little context on what a population portion is. I put in this little tidbit here about an election year. This is where we kind of, I think, tend to see this the most, especially in a news cycle, is that during this election year, they have these polls, they have these reports where they say, you know, this candidate has 40% of the vote within 3 percentage points. All right, so they'll say that that's where the candidate is polling at. And this 3 percentage points is essentially the confidence interval. What they're really saying is they're, however confident. Here I noted that typically those confidence intervals are calculated at a 95% confidence level. So they're basically saying they're 95% confident that the candidate's votes, the population proportion that's voting for the candidate is between 37% and 43%, because that's 3% below 40 and 3% above 40. All right, so we see that here. If you want to take a moment to read through that beginning, that's essentially what they're saying when they say that they have 40% of the vote within 3 percentage points. That is a confidence interval. All right, in these situations with proportion, a population proportion, they have only two options. If you think back to our chapter, what chapter was that? Chapter 4 era. All right, we were discussing situations that had only two options, yes or no, this or that. In these cases, talking about maybe a presidential election, you're either voting for that candidate or you're not voting for that candidate. This is called a binomial distribution. All right, and just take a moment to remember what that distribution was. X was binomially distributed, and the two variables that were important were N and P, the number of trials and the probability of success. N is the number of trials, P is the probability of success. And remember that Q, the probability of failure, was the complement of success, 1 minus P. Again, because there's only two options. Either you have success or you have failure. So together they have to equal 1 or 100%. All right, so that's where that formula is coming from. Like I said, it's a little similar. It is similar, not just a little, to when we did a confidence interval for the sample mean, right? X bar minus E to X bar plus E. But here we're not talking about a sample mean, confidence interval for a population mean, where we use the sample mean as the middle there. Now we're going to have this estimation for a proportion. We're going to be talking about the estimation for a proportion minus an error, the estimation for a proportion plus an error. All right, so this sample proportion we denote as a p hat. It's not a bar, it's a little hat. All right, we have our p hat, and that p hat is calculated with the number of successes out of the number of trials. So I'll write it over here too. Number of successes. If we were talking about how many people were voting for a president, that's how many people would be voting yes. And number of trials would be how many people that you asked. So the number, so let's say I asked 50 people and 30 say they are voting for the president. That would be my p hat there. That would be my estimation for the population proportion. All right, I'm going to just combine everything on this first page to one video, so I apologize if it is a little bit long. just talking through all the vocabulary before we get into our examples. So again, like I kind of noted earlier, the confidence interval is very similar to when we made one for a population mean, but here we are doing it for a population proportion. So we have our estimate for the proportion, our p hat minus the error, comma, p hat plus the error. And that's in parentheses. That's our interval notation. Oops, I don't know, put that extra parentheses earlier. That's in interval notation. So this is the lower bound and the upper bound for that interval. That's just how we find those. And the error bound formula is going to use a z-score, similar to how we did it earlier, but there's not a standard deviation situation here. Instead of multiplying by the standard deviation over the square root of n, we have a full square root. So notice that that's a really tall square root. Everything I write is inside the square root. We have p hat times q hat over n. That's all inside the square root. And that's a product when they're written next to each other like that. P hat times q hat over n divided by n. All right, I added this note. Notice that this is a z-score. This is the same as when we did the confidence interval for a population mean and we knew the population standard deviation. All right, the reason this is because binomial distribution, as long as we have this good relationship, our rule of thumb, which I'll discuss here in a minute, is true, then we have a normal approximation when it comes to binomial distributions. All right, so again, by using this, we are taking that liberty of saying that binomial is approximately normally distributed. So just to make sure that that rule of thumb is close enough, is good enough, we want to check these two things. Need to check that n times p is greater than or equal to 5. And n times q is greater than or equal to 5. This is similar to how we had in chapter 7 that n was sufficiently large, right? N needed to be like bigger than 30 for us to be able to use that approximation for a normal distribution. Well, here we're kind of confirming that p and q aren't ridiculous in like the estimation for p being way too big or way too small, as well as n being big enough to kind of balance out those two pieces there. So again, this is just something we need to check before we assume that normal distribution and kind of follow these formulas up above. So just make sure to put those in your brain somewhere, tuck that in, and I'll try to confirm these as we go through our examples to make sure that we are good to go in using these formulas up above.